This is part 3 of proof by contradiction. We're going to introduce some new definitions and do some proofs related to these definitions. So a real number x is rational if x is equal to a over b for some integers a and b. In other words, x is in the rational numbers, that's denoted by a bold-faced Q, if and only if there exist a and b in the integers such that x is equal to a over b. So that is the definition for a rational number. Just remember that the symbol for a real number is bold-faced R. And a real number is irrational if y is not equal to a over b for any integers a and b. So we could write that y is not in the rational numbers if and only if y is not equal to a over b for any a and b in the integers. We could also write that as there exist no integers a and b, so there exists no a and b in the integers such that y is equal to a over b. So those are two ways we could write that. And again, we can write that as y is not an element of the rational numbers. There isn't kind of a standard letter to denote the irrational numbers typically. Okay, and recall that the real numbers are composed of the rational numbers and the irrational numbers. So these are irrationals. So any real number is either rational or irrational, but not both. Okay, so which of these real numbers are rational? So let's look at this example. We've got 0.403, 32, square root of 2, and 0.12 repeating. So this is 0.121212 forever and ever and ever. So think about each of those and whether you believe they are rational or irrational. And if they are rational, then try to write them as a over b for some integers a and b. So give that a try, and we'll talk about it in a moment. So pause, and we'll talk about it in a moment. Okay, so which of these real numbers are rational? Well, 0.403, we could write that as 403 over 1,000. That would be one way to write it. And where 403 and 1,000 are both integers. So that tells us that yes, 0.403 is in the rational numbers. It is rational. Note that the representation as a fraction of integers is not unique. So 0.403 is also equal to, say, 4030 over 10,000. It's also equal to, 806 over 2,000. It's also equal to, there are many different representations of 0.403 as an integer divided by an integer. So this a over b is not unique. It just matters that there exists some a and b, some integers a and b such that this is true. Okay, how about 32? Well, yes, 32 is rational because we could write it as 32 over 1, and both 32 and 1 are integers. We could also write it as, let's do a little separation here, we could also write it as negative 64 over negative 2. Those are both integers, and there's lots of different ways, again, that we could write 32. So yes, 32 is a rational number. It is also an integer, but we know that the rational numbers are a subset of the integers. Sorry, the reverse. The integers are a subset of the rational numbers. Any integer x is also a rational number for this reason above, that any integer can be written as itself divided by 1, and therefore it is rational. Okay. How about square root of 2? Well, square root of 2, you may know as not being a rational number. It's sort of famously irrational. And we will actually prove this in a moment. So we will prove this. So just based on the definition, there's no very obvious way to say, hey, this is not a rational number. Like, it's much easier to directly show something is rational by writing it as a ratio of two integers. And to show that something is not rational, you have to show there exist no integers a and b such that square root of 2 is equal to a over b. Obviously, that's a little harder to show, but we will prove this in a couple moments. Okay, and lastly, 0.12 repeating. This actually also is rational, so 0.12 repeating is in the rational numbers. Let's show that that's the case. And this one takes a little bit more work, so we'll show this right now. So let's consider 0.12 times 100. 0.2 repeating times 100. So what is 0.12 repeating times 100? Well, that's just moving the decimal place over 2 places. So that's 12.12 repeating. Okay, let's subtract the 0.12 repeating from both sides of that equation. And if we do that, then, well, here we had 0.12 repeating times 100. We're taking one of them away, so there are 99 left. And so we have 0.12 repeating times 99 is equal to, well, 12.12 repeating minus the 0.12 repeating. All we're left with is 12. And now what were we trying to do? We were trying to write 0.12 repeating as a fraction of an integer divided by another integer. And so at this point we could divide both sides by 99. And if we do that, then we get 0.12 repeating is equal to 12 divided by 99. So we have written 0.12 repeating as an integer divided by an integer, so where 12 and 99 are both in the integers, and therefore 0.12 repeating is in the rational numbers. This example above alludes to another definition, equivalent definition of being rational. So x is a rational number if and only if, as we saw, there exist a and b in the integers such that x is equal to a over b. It's also equivalent to x is rational if and only if the decimal representation of x, so the decimal representation of x either terminates or repeats. So either terminates, that is, ends, or repeats. And so this would be an example above, 0.12 repeating forever repeats, and it can be written as 12 over 99, whereas anything that terminates, if it ends, like 0.021, that has a decimal representation that ends, that could be written as 21 over 1,000. Okay, let's now prove that the square root of 2 is irrational. So we are going to do this proof by contradiction. So proof by contradiction. All right, so we are going to assume that the original statement is false. So suppose that square root of 2 is rational. Now, by definition, that means that there exist integers a and b such that square root of 2 is equal to a over b. So that is the definition of being a rational number. We're actually going to add one more element to this, where a over b is fully reduced. So by fully reduced, that means that a and b have no common factors. That is, a and b have no common factors aside from 1. We could say that. We could also say where a and b are not both multiples of 2. Why is that acceptable to write? Well, if a and b were both multiples of 2, then we could reduce the fraction, and so we could divide both the top and the bottom of that fraction by 2, and they would still both be integers, and so we could then still write square root of 2 as some other integers where a and b were not both multiples of 2, or r and s were not both multiples of 2. Okay, so let's see where we can go from here. Right now we're talking about something that is a square root. Often in mathematics, if you've got an equation with square roots or fractions or things like that, you might want to try to do something to simplify the equation. So something we could do at this point is square both sides of that equation. Squaring both sides of square root of 2 is equal to a over b gives, the square of square root of 2 is just 2, is equal to a squared over b squared. And now we could, again, trying to sort of simplify that equation. This implies that if we wanted to multiply both sides by b squared, 2b squared is equal to a squared. So we've taken the original equation, square root of 2 is equal to a over b, and algebraically made it a little bit simpler by writing it as 2b squared is equal to a squared. All right, what could we observe at this point? Well, note that since a squared is equal to 2b squared and b squared is an element of the integers. We know that b squared is an element of the integers because b was. We see that 2 divides a squared. 2 divides a squared. Also, since 2 is prime, we can reach back to a theorem that we proved in the last video. So since 2 is prime and 2 divides a squared, 2 also divides a by a previously proven theorem. So we proved this in the last lecture, and if you've already proven something, you can always refer back to it. Okay, so 2 divides a. Now, since 2 divides a, that means that a is equal to 2 times k for some integer k. Now let's look back at the equation that we had above. Let's again consider the equation we had above. 2b squared is equal to a squared. Well, now substituting gives that that's equal to 2k squared, which is equal to 4k squared. Dividing both sides of this equation by 2 gives b squared is equal to 2k squared. So that is what this gives us. And now, what do we see? We see that 2 divides b squared. And again, since 2 is prime, 2 also divides b, again by that previous theorem that we've already referred to. And So we see that 2 divides A and 2 divides B, contradicting that A over B is fully reduced. So we have reached a contradiction, and so we have contradicted our original statement that there exists integers a and b such that square root of 2 is equal to a over b, where a over b is fully reduced. So this was a really important crux of our argument. Also an important piece of our argument was that we had this previous theorem that if a prime divides some integer squared, it must also divide the initial integer as well. That is not true if the number 2, or if the number is not prime. So we can only show that for sure for prime values. So, what was the whole argument here? We suppose for contradiction square root of 2 is rational. We then use the definition plus a little more. So we use the definition square root of 2 is equal to a over b. And we are using this extra trick that is a trick that I would not expect you to come up with on your own, but there will be a homework problem where you have to sort of do a modified version of this. And so we are now going to realize a contradiction in showing that square root of 2 cannot be equal to any integers a divided by b, where a and b are not both multiples of 2. If that's not possible, then square root of 2 cannot be written as any integer divided by another integer, because if it could, then we could reduce it down to a case where they were not both multiples of 2. So this is probably the first proof you've seen that a number is not rational. And notice that, what did this rely on? Again, the definition of a rational number, as well as the fact that 2 was prime. So the only thing that was special about 2 was that it was prime. And so what we have actually shown is we have shown that if p is prime, then square root of p is irrational. So we have shown that if p is prime, then square root of p is irrational for any prime p. That at least shows us there exist infinitely many irrational numbers. So there exist infinitely many irrational numbers. The square root of any prime is irrational, and we proved also in the last video that there are infinitely many prime numbers. There are many, many, many other irrational numbers aside from square roots of primes, but at least now we know there are infinitely many of them. Okay, let's do a proof. So as I said, the last proof is not one that I would expect you to come up with on your own instantly, as I said, but it is a very famous proof and something to read over and think about and make sure that you understand fully. Let's look at another one, and this is one that I think you could do on your own, given what we have so far. So if x and y are rational numbers, then x plus y is also rational. For practice, let's actually do this proof twice. So let's do proof by contradiction, as we have been doing. Let's also do it directly. When you're thinking about a proof by contradiction, we have to think about what is the negation of this entire statement. So negating this entire statement, what would that look like? So give that a shot, and we'll look at it in just a moment. Okay. If x and y are rational, then x plus y is rational. Let's first do this proof by contradiction. So we would suppose for contradiction the negation of the original statement. Let's on the side think about what the negation of this statement is. So this is currently an if-then statement. In other words, this is a P implies Q statement. And recall that the negation of a statement P implies Q is P and not Q. So we are going to assume that the first part is true and the second part is false. So suppose for contradiction that x and y are rational, but x plus y is not rational. So that is P and not Q, that the if statement is true, but the then statement is false. Okay, so if that's the case, what kind of contradiction could we arrive at? Well, one thing that we could arrive at is, so here we are assuming that x plus y is not a rational number. We could show that x plus y is rational, and something cannot be simultaneously rational and irrational, so that would be a contradiction. So that could be our goal. So let's try that goal. Again, this is just my scratch paper over on the side. Okay, so since x and y are in the rational numbers, this means that x is equal to a over b and y is equal to c over d for some integers a, b, c, and d. And actually, I'm realizing that I have to go back and edit a part of the definition. What can we not do when we're thinking about rational numbers? We can't divide by 0. So where b and d are both not equal to 0. Okay, so sorry about that. I will edit above. All right. Anyway, so now let's consider x plus y, that's equal to a over b plus c over d, and we could simplify that. That's equal to, if we want to add two fractions together, we can get a common denominator, so that's equal to a times d over b times d, plus, get a common denominator on the other side, b times c over b times d. Now we can add those two fractions together. That's AD plus BC over BD. And what do we see? That is equal to, this is where AD plus BC is an element of the integers, because each of those individually was an element of the integers. And so multiplying two integers gives an integer, adding two integers together gives an integer, so that is an integer. And BD is an element of the integers, and BD is not equal to 0 since B and D are both individually not equal to 0. Okay, so we have arrived at the contradiction we were hoping for. We see that x plus y is in the rational numbers, but x plus y is not in the rational numbers by hypothesis. These two things cannot simultaneously be true, so this is a contradiction. And because the negation of the statement was false, that means that the original statement must be true. Okay, let's consider a direct proof of this. So proof direct. So if we're doing a direct proof, then we would say, okay, suppose that the original statement is true. Suppose x and y are rational numbers. Then x is equal to a over b and y is equal to c over d, where a, b, c, and d are integers, and b and c are both not equal to 0. Okay, so that is just the definition. Basically, our proof is going to look almost exactly the same as above. So observe that x plus y is equal to a over b plus c over d, which, as we saw above, is equal to AD over BD plus BC over BD, and that's equal to AD plus BC over BD, where AD plus BC and BD are both elements of the integers, and BD is not equal to 0. Since B is not equal to 0, D is not equal to 0. Should be a D. Okay, so we have shown that x plus y is an element of the rational numbers by definition, and we are done. So observe that in this case, a direct proof is actually an easier proof. So this direct proof is actually a bit easier in this case. However, we can prove it using proof by contradiction. We could also consider doing this as a contrapositive proof in this case. It's an if-then statement. So an if-then statement can be proven using, we could theoretically prove it directly, or using contradiction, or using contrapositive, but sometimes one method will be easier than the other. In this case, direct proof is the easiest way to go,